Hello everyone, I am happy to present this work on behalf of my team. I'll be presenting SuperServe, a fine-grained inference serving system for unpredictable workloads. So there have been several applications that use AI. Two of them are listed here. Self-driving cars, like they have a bunch of sensors, onboard GPUs, and they are continuously doing planning and perception. Chatbots too, they are deployed in the data centers. You have large language models, etc., that are continuously processing queries, right? So what do these applications usually require? They want timely and accurate responses. So in the case of autonomous vehicles, even a few milliseconds of delays in perception or planning can be very critical in terms of safety. Chatbots, the users expect responses that are accurate, good, almost in near instantaneously, right? So the delays will hurt the user experience. And the traffic from these applications is usually very dynamic, right? So it is unpredictable. There have been several works in attempting to predict the traffic, but they are not very, very useful. The systems that are deployed for these applications, they must be frugal with their resources, right? So without over-provisioning or without wasting resources. So the goal of ML inference serving systems is threefold. They need to strike a good balance between latency, because the requests are latency critical. Their requests need to be provisioned with highly accurate models, and you also want to focus on resource efficiency because that directly ties into the deployment costs, right? So this creates a very interesting trade-off space in ML serving. If you're going to provision only high accuracy models, they typically require higher latency, so you're going to miss more latency SLOs. So you're going to reduce the latency SLO attainment. You can bypass this by provisioning more and more resources, right? So you can have more GPUs deploying the models. You will get a high latency SLO attainment, but you're going to be bad on resource efficiency, right? So this creates a very interesting trade-off space. Along with this, a key question is that how do you efficiently navigate this trade-off space, but in the presence of highly unpredictable workloads, right? So we discussed that the client traffic is unpredictable. What does it look like in real world, right? So the challenge is these bursty workloads. Over here, you can see a trace derived from Microsoft Azure functions, where on the y-axis, you can see that the request throughput increases drastically from 6,000 requests per second to 8,000 requests per second really, really fast. And even the peaks that you see, they are in tens of seconds, right? So tens of seconds, you will go from 6,000 requests per second to 8,000. And this, your system is expected to handle all of that, right? So these are what we call bursts. And the bursts are actually adding complexity to the already non-trivial trade-off space that we have with accuracy, latency, and resource efficiency. And your system is expected to absorb all of these bursts, right? So let's look at how prior inference serving systems tackle this. One approach is you have fixed models that are going to serve the entire workload, right? So the models are decided a priori, while the deployment for this is simple because you have already decided the model. This is suboptimal with respect to accuracy and latency trade-offs. These include systems like Clipper, Infoline, Clockwork. The second approach, or the newer systems, they actually allow you to switch models during the workload, right? So there is a policy which is going to govern which models to serve at what points of time. So this will give you better accuracy latency trade-offs, but they incur higher resource costs, and this includes systems like Infas. So let's look at why, how these systems perform and why are they not optimal, right, for the trade-off space. So first we look at why static choices or fixed model choices are bad. On the same trace that we have, suppose you want to provision for this burst that you have around 8,000 requests per second. One way of doing that could be that you provision it with a low accuracy model which has high throughput. So you will be able to sustain the peak of requests that arrive. So the green is actually the area of the request that you are able to successfully deliver within the latency SLO, right? But the con of this approach is that you're going to serve all the requests with very low accuracy. The other approach is that you take a higher accuracy model, but as we know, with the higher accuracy model, you're going to have a lower throughput. So the green area now is much lesser. You can see that you are going to miss many of the deadlines of the request, right? So this also is bad. So now we move on to systems that allow you to switch between different model choices, right? So as we know, switching between different models allows you to maximize the accuracy latency trade-off space, and let's see how the current systems do it, right? So in this graph, if you see the lower left corner, you can see that the throughput at this point is low, right? So you can afford to provision high accuracy models while serving the latency SLOs. And when the peak arrives, you want to switch to high throughput models with low accuracy to meet the latency deadlines, right? But I would like to draw your attention to the bursty nature of this trace again, right? So if you look at these two red dots, they are fairly close to each other, and they go from a very like a moderate throughput to a high throughput fairly fast, right? So it's not just sufficient to switch the models, you need to switch between these models very fast, right? So are the systems able to do that? We tried to answer this question. So in the current systems, the model switching would look like this, right? So you start with the trace with a medium accuracy model. You see that a burst has arrived, so you switch to a low accuracy model. And then further, as you go along, the throughput required is lower, so you switch to a high accuracy model, right? So this approach allows you to reach a better latency accuracy trade-off, but it is coarse-grained, and there is performance left on the table that you could have capitalized on, right? So you need an approach that is even more suitable for rapidly changing or bursty traffic. So why are the current systems performing this way? Because you can either have all the models in the GPU memory, which allows you to switch between the models trivially because all of them are in memory, but this has a very high memory cost, so it's low on resource efficiency. The other approach is that you need to switch between CPU and GPU models, right? So you have models in the main memory, you keep swapping them in and out of the GPU as and when you require, right? But this movement of models itself incurs a very high latency, and it's almost comparable to the inference latency in tens to hundreds of milliseconds, and this negatively affects your throughput and the accuracy that you can achieve, right? So now we introduce SuperServe, an inference serving system that is built around catering both latency accuracy trade-offs and for bursty workloads, right? So we do this by two components. First is the mechanism, which is the SubNetAct, which allows you to nearly instantaneously switch between models with very less memory overhead. Second is the policy, which is SlackFit, which is a fine-grained reactive scheduling policy designed to optimize, to maximize latency accuracy objectives, right? So with that, you see that the graph that we showed earlier, you will be able to reach performance such as this, where you're very, very quickly switching between low accuracy, high accuracy models, and you're also able to meet the latency SLOs, right? So first, I would like to explain a bit about SubNetAct, which is the mechanism that enables this very fast model switching. So we leverage prior ML works which develop super networks, which are basically pre-trained once-for-all models, which have a large number of subnetworks that can be extracted and deployed by the user, right? So from this large super network, you can extract different subnetworks, which are different with respect to their latency and accuracy, and these can be deployed for different latency budgets. We leverage this to innovate and use SubNetAct, which actually uses the property of this super network, which is that within these models, there are many shared layers and non-shared layers. So if we insert operators to dynamically activate and switch between these shared and non-shared layers, you essentially activate different models in less than 1 millisecond, right? So this allows us to switch between models very fast, and this property of very quick model switching is leveraged by SlackFit, which is a fine-grained reactive scheduling policy to maximize latency and accuracy requirements, right? So SubNetAct, it does fine-grained scheduling, and it is doing two choices. One is which model to pick, and the second is what batch size do you want to deploy the request with. So first we attempt to frame this as an optimization problem, which is NP hard. So over here, you see that you want to maximize this, this set of constraints, where you have the expression trying to maximize which queries you want to meet the deadline for with what batch size and what accuracy. Obviously, these are too detailed for a talk right now, but you can look at these constraints that are going to specify whether the query needs to be placed on what deadline it can meet, right? But since ILP is very difficult to solve at the critical path, we come up with a heuristic which operates on just the Pareto optimal subnets, which try to maximize the accuracy given a latency, and they operate on the slack, which is the remaining time for the most urgent query based on the EDF queue, right? So over here, if you see the red dot, you have a decent amount of, you have low queuing delays, right? So you have more slack, and with this, you're able to provision a higher accuracy model. When you reach the high throughput area, you have more queuing delays, so you have low slack, and you switch to a low accuracy, high throughput model, right? So just a high-level overview of the architecture. You have the client, router, workers. The client submits queries to the router, which is enabled with SlackFit. It has the super network profiles, latency accuracy profiles. It does the scheduling. It sends the batch to the worker, which then activates the subnetwork instantaneously and serves the request, right? And yeah, so finally, experiments. We evaluate how does SuperServe do when you are giving bursty traffic, how does it perform on real-world traces, and we compare against baselines, which are both fixed models serving, such as which are models that are going to serve the entire workload, and the model switching approach of Inference. So SuperServe on bursty traffic, we evaluate it on multiple traces. Over here, you can see along the x-axis, you make the traffic more and more bursty, which is the peaks are higher and the troughs are even lower. And along the y-axis, you increase the ingest rate, which is the mean serving throughput, request throughput. And you have mean serving accuracy versus SLA attainment. For this talk, I'll just focus on the bottom right corner, the plot. And obviously, you want to be at the top right, which is going to maximize the mean serving accuracy and the SLO attainment, right? So SuperServe on this traffic, you can see that the fixed accuracy models, they are only partly able to satisfy the latency accuracy requirements of the workload, while SuperServe is at the top right, which meets 99.92% SLO, and it gives you 4.11% higher accuracy. And yeah, it can also increase the SLO attainment given a level of accuracy. On the real world MAF trace too, we find that it is able to give you 4.67% higher mean serving accuracy at a very, very high SLO attainment of 5 nines, 99.999, and you are able to increase the SLO attainment by 2.85x at a given, finally, to conclude, this is like a plot to show that how does SuperServe react when there are bursts. So if you look at the topmost, this is the arrival rate. In the lower part, you see that the SlackFit uses SubNetAct to make fine-grained decisions to instantaneously switch to lower accuracy models when the burst arrives, and it also switches to higher batch sizes to maximize the throughput, right? So this enables SuperServe to absorb the burst while switching to a lower accuracy model and sustaining the request rate, right? Yeah. To conclude, we highlight key issues in ML serving for bursty workloads. We innovate on super networks to produce SubNetAct, which inserts operators to enable subnet activation in less than 1 millisecond. SlackFit leverages this mechanism to produce effective schedules to maximize both latency and accuracy SLOs. And SuperServe as a system, it increases the accuracy by 4.67% over the baselines, and also can increase the SLO attainment by 2.85x at the same accuracy. Yeah, thank you.